Hello everyone, thank you for joining us for today's webinar, using inertial measurements to enhance LiDAR point cloud accuracy. I'm Jeff Bestbrode, Marketing Executive here at OxTS Survey. Presenting the webinar today, we have Jacob Amaker, who is one of our product engineers. And alongside Jacob, we also have Dieter Gabriel, who is Velodyne LiDAR's EMEA Marketing Manager. We've been working closely with Velodyne LiDAR now for quite some time, so we're delighted to be able to prize Dieter away from his busy schedule to share his thoughts with us today. So during the session, we'll be taking a closer look at how, by using inertial measurements alongside Velodyne LiDAR sensor data, you can enhance the accuracy of your point clouds. During the webinar, we will cover a number of topics that we hope will be useful for your day-to-day survey and work. The presentation is due to last approximately 40 minutes, and there will be some time for questions and answers at the end if you would like to join us for them. If you would like to ask any questions during the presentation, you can ask these using the drop-down menu, which is located at the bottom of the panel on the right-hand side of your screen. If you do ask any questions here, we will answer them at the end of the presentation. We will aim to get through as many questions as we can during the session today. But if we aren't able to answer your question, then we will reply to you after the presentation personally. Just a couple of last things to say. The webinar will also be recorded and a copy sent out to everybody who registered tomorrow. Yeah, without further ado, I'll hand you over to Jacob and Dieter.
All right, thank you, Jeff. So thank you everybody for joining this webinar. And we're essentially going to be talking about using LiDAR with an INS and getting the most out of such a system. So going to be talking about accuracies, hardware and software setups, INS accuracy as well as LiDAR accuracy in particular, and also bore sight calibration, which is essentially a calibration of inaccuracies in the angles between the two devices. So we're going to be looking at all of these throughout.
Yeah, hello everybody. A warm welcome from my side as well. I'm Dieter Gabriel. I'm with Velodyne as Marketing Manager for Europe and Middle East region. Yeah, and I'm really pleased to present in this webinar today. We did it before actually, so it's not the first time that we do a webinar together. Well, and it's always a pleasure, so I'm really looking forward to the webinar now. Yeah, maybe I just make a start here. So talking about combination of LiDAR data and inertial navigation systems. So our LiDAR technology uses eye-safe laser beams to create a 3D representation of the surveyed environment. But if you want to work with that data, you usually need to rely on the geometric precision of these data sets. Well, and it is obvious that it makes a difference if you look at a raw data set or if you look at process data, whereby I mean geometrically rectified, or let's say georeferenced data. And it's quite easy to understand the difference between a raw and a georeferenced data set. If you look here at this slide, the blue image illustrates our raw LiDAR data output, how it looks like. And to come to results as shown here in the black and white pictures, you need to georeference the data, usually by means of a GPS or INS system. So it's pretty clear when you look at the difference between the raw data, what you get from a LiDAR sensor as the constant output that you see here marked in the blue lines. And if we compare it to the accumulated georeference data, for instance, that you see here in the upper left part of examples. So you can see, for example, the trees and the pavement markings here are filled in, and this is what makes up a georeference data set, so that everything is closed, get a dense representation, and you can work with that data. It's obvious what a big difference it means to the raw data set. So what is now georeferencing? So on the one hand, we have raw data output from one of the LiDAR sensors, and you want to end up actually with data that you combine with a map, or that gives you kind of map accuracy. So each frame or shot of your LiDAR survey data should be paired to global position and orientation given by navigation data. And this is what you get when you combine during the survey the sensor with the OxTS navigation solution. And precision of the LiDAR data is important, but also the navigation data precision is absolutely necessary to end up there with a good calibrated approach. You get a combination of these sets, you get really combined data that you can work with. Principally, if you look here at this example, it may sound trivial. You have the LiDAR data, you need some georeferencing, you put it together, and the scope of the following discussion now will be what's behind it. And it's not so easy at first glance. And what is necessary, what makes up a good system to come to really georeferenced, reliable data. And with that, I'd like to hand over to Jacob again.
Thank you, Dieter. So I'll now be talking a bit about the accuracies that the INS contributes to. So we're going to start with IMU accuracy. So an INS system typically would be made of an IMU, an inertial measurement unit, and a GNSS system. And I'll be talking about that after this. So the IMU is essentially, you can think of it as a collection of gyroscopes and accelerometers measuring angular rates and accelerations on each axis, 3D axis, and it's going to be outputting these, and they can be integrated to give you velocities and integrated again to give you a trajectory. So when you're thinking about an IMU, you'll usually see some kind of random walk or some way of expressing the intrinsic stability of the measurements that you're making. But you'll also see on a INS data set, data sheet, something like heading, pitch, and roll accuracy. So you can see these at the bottom. So this is from a XNAV 650 INS unit. You can see something like 0.1, 0.05 degree of accuracy in the IMU data. And this is very, very important, as I'll go on to show you. But these come from an INS, and these are not just IMU accuracies. So they come from when you have some constraint on the heading of the INS, which is given by GNSS data. So you have your GNSS heading, which has some kind of error, and you also have the IMU, which is measuring changes in that orientation, in that heading, with some kind of stability. So why is this so important? So the reason this is so important for LiDAR survey is because we are looking at things in the distance, and we are using the IMU and the heading lock to see these units and to see these objects from some distance. And the error in their position is, of course, highly sensitive to the error in your angle that you've measured. So you can see this simple diagram here. You've got an error in your in your angular measurement, and you always have some error. And this is exacerbated over range. So a simple calculation would be to multiply this error by the range. So if you're looking at something, I've got an example calculation at the bottom here. You can see if we're looking at something 50 meters away, then in one axis for a 0.1 degree error, you can get something like 10 centimeters of position error in any surveyed object. So you can imagine this can often be a bottleneck for the accuracy of the total system. And since this is just one error, this is going to compound with others. So IMU accuracy is extremely important, and we'll be talking a bit more about this throughout the webinar. So as I mentioned, an INS system will also have some kind of GNSS receiver. Usually it's using GNSS for its position localization. So satellite signals are intercepted and triangulated to give some kind of global position for the INS. So we have the antennas. So you have your box, which is your INS, but the box is reliant on your antennas, which are intercepting these satellite signals. And then those satellite signals, triangulated, will give you some kind of position. And a significant source of error will come from the quality of those signals, or the ability of the antennas to view those satellite signals. So just like with the heading, the IMU is not able to know where it is pointing or where it is. It is only able to measure changes. It is only able to measure accelerations and angular rates. It doesn't have some kind of ground truth, but the GNSS is what is providing that. So you want to know exactly where you are, and then the IMU helps you to understand how that is changing. But if the GNSS is not good, if you've got, say, objects in the way, you can see on the right here, you've got buildings, which not just block signals, but signals can bounce off and give you errors in the position to the satellites. And you can see what the difference between a GPS system only and a GPS and GLONASS system gives. And so if I just explain what that means, so these are two different satellite constellations. It essentially means there are double the number of satellites available for the GNSS system in the red line, which you can see is smooth and is what you would expect. But with the GPS only line, not enough satellites are being seen. And so you need about 6 satellites to get the highest grade of accuracy in your position. So you want to get that centimeter level position, but you need 6 satellites at least to be not just in view, but to be tracked. And you can see when that does not happen, the INS is relying more on the IMU than the GNSS. And so you can see how the blue line jumps, and that is because without enough satellites, the system is only able to know its global position to something like more like a meter or half a meter than the centimeters that you would like. So not only do they use GNSS and IMU data, but INS systems are taking in this data from both sources and are able to combine them intelligently. So you can see what an important thing this is, that these two different sources of measurements are kind of playing to each other's strengths and weaknesses. So you've got the IMU is measuring changes, and you've got the GNSS is localizing the heading and the position. So in this diagram at the bottom, you can see how in this terrain where you've got your GNSS, signals which are being heavily obstructed and distorted by the tall buildings, the reflective buildings, and all sorts going on around it. You can see the huge errors that can occur in GNSS data. But when you've got the IMU, the INS is able to understand that it is actually not moving, say, several meters to the left or the right. It is able to reject bad GNSS data, as well as using the GNSS data to reject IMU measurements that are caused by the internal or the intrinsic instability of the IMU. So by combining the data streams intelligently, you're able to make a lot more of the data. So for example, you can run a navigation engine which is able to utilize each individual satellite as opposed to only using a outputted position that you need 6 satellites for example. Or you're able to put in different parameters. So this here is a screenshot from a software where you can input the distance of the INS to axes on the vehicle, and that is able to really help the navigation engine to reject IMU random walks that are not in keeping with what it would expect. Here is another example. So you can see this is our advanced smoothing algorithm. This is essentially, you can see left to right, it's removing these jumps in the data. And this is similar to the previous picture with the GPS and the GLONASS, except in this case, we are in a tunnel, so there's no GNSS here. And what we are looking at are post-processed data sets, the same raw data, just processed with and without this advanced smoothing algorithm. So INS systems are able to do this by combining a process of the raw data forwards and backwards in time, and when it combines them, it has to understand which one is more accurate and which one to go with. And this can, in cases such as a tunnel where there's no GNSS, the navigation engine does not know which one to choose. And that's why we've developed this algorithm, which is able to intelligently smooth out the data. So you get rid of these lines if you are looking to do an application like object recognition, where you need to be able to see the lines and your AI to recognize them. You would want something like this. On top of that, INS systems are able to take in additional data streams. So you don't just need the IMU and the GNSS. You can also work with other data streams. So for example, we've worked with a wheel speed sensor for this data set here. So this is a LiDAR survey of a neighborhood. And you can see on the right here where this section is red, the GNSS has been manually turned off. And the red is representing that it is in the lowest accuracy mode. So we're looking at something like 0.5 meter of position error because there's no GNSS. And the test here that we've done is how much improvement does a wheel speed sensor give? So wheel speed is measuring the speed of the wheel or the speed of the vehicle, and that data is fed into the navigation engine of the INS, and you can see the kind of difference that it makes. So you're seeing blue as the highest, so that would be something like 5 centimeters of precision in the point cloud, and you can see the big difference. It makes not only the section without GNSS better, but it actually improves the whole point cloud, as you might expect. And here's just a close-up, so you can see these houses and these objects. You can see there's There's some double vision in some different objects like the sides and the sides of the houses and the lampposts and things like this. And there's considerable blurring, but after applying the wheel speed is able to tell the INS actually it's not moving around so much like the GNSS, like the IMU is telling it, because the IMU is inherently unstable and moving about. The wheel speed is able to sort of act like a GNSS, saying actually it's going this speed, so we don't need to think that it's moved, say, half a meter, if you see that.
And this is a really great example, Jake. So it really highlights what makes up the difference between a poor quality data set and such an enhanced point cloud relying on the processing engine from your side. So it's really impressive.
Yeah, exactly. So this is done with the Velodyne VLP16 system, and you can see the kind of data that if you're doing a survey in something like an urban environment where GNSS is going to be quite poor, then a different data streams such as a wheel speed sensor can really aid the navigation engine to make sure that the whole thing is reliable. So we have a poll question now, so I'll launch that. So we want to just get an idea of what kind of vehicle people are using out there. So a lot of people are using UAVs, a lot of people are using cars as well, and all different sorts. And different parameters can be fed into a navigation engine depending on the vehicle, and different LiDAR are suitable for different applications on different vehicles. Okay, I'll leave that for a couple more seconds. So I'm just showing the results now. So it might be what you expect, something like most people using a drone in a car, and then we've got some backpack and boat surveys, and some others as well. Might be some aerial surveys there. So thank you everybody for that. So I'm just going to talk a bit about boresight calibration before handing back to Dieter. So the boresight calibration is about the relative rotations between the two devices. So you've got an INS and a LiDAR, and they have different coordinate frames. So the LiDAR is measuring the positions of objects relative to itself, and the INS is measuring its global position and orientation. And then, of course, you need to apply some transformation between the two in order to combine the data. But unfortunately, the transformation has to be known very precisely. So in exactly the same way as we saw with the IMU error, any errors in this orientation is also going to be exacerbated over range. And so it needs to be known precisely, and that is often very difficult. But we have developed a way to calibrate these angles, and I'll just talk you through that now. So firstly, why is it such a problem? So this diagram, this applies similarly for the IMU inaccuracy as well as the boresight misalignment. And so you can see from different perspectives, if you've got a different error, or if you've got an error in your setup, you're going to be seeing objects differently depending on your perspective. So for example, you've got this blue and this red perspective, and you're seeing not just one lamppost, but you're actually seeing two lampposts. And I'll show real life examples of this in a second. And you're also seeing they will be distorted, so there'll be slightly different sizes different orientations, and they might be entirely separated. But also, you might be adding up not just the blue and the red, but everything in between. And so on the right, when you've added up those LiDAR frames with the navigation data, like we showed at the start and Dieter explained, you actually get a kind of composite image which is blurred. And so you might have a very wide lamppost and unrecognizable details on different objects. So our solution is it's actually very simple from a practical point of view. So we have this solution where you can survey these two targets. These are very simple targets. They are just reflective targets. And this can take 5 minutes. And it can be added onto your survey, start or finish, or separately. And you simply let our software do the work. You just tell the software where the targets are, and it will work out the calibrated setup angle. So an example you can see here, you can see these angles that were put in at the start, 180, 0, minus 90. And after calibrating, you can see the points of a degree that it's calibrated to. And so if you remember that calculation at the start with the 0.1 degree error, giving you something like 10 centimeters of point position error, you can see how important the bore sight calibration is as well. So if you have the IMU accuracy plus this error contributing to the same point cloud, you're going to have an error that is very quickly building up to remove details that you would want. So here's another example of the bore sight calibration results. So this is before calibrating, and you can see from this drone survey, there's a van at the top here in red, there's a car on the left, and there are the two bore sight targets that I mentioned that it has flown over. And you can see, of course, that this is very blurry and that there are two cars instead of one. But after applying the calibration, so this is the same raw data, but applying different angles between the two coordinate frames and using our bore sight calibration technique in our software, you can see the huge difference that this makes. So just like I showed in that diagram with the lamppost, that might appear as two lampposts, we've got the car which is appearing as two cars, and significant blurring throughout. So this is a really nice example. So it's a cross section of a road. So the road is down here. You can see there's a pedestrian, and this is a building. So we've got two perspectives, you might say. So we've got a red and a blue perspective. The blue is going down the road one way, and the red is turning around and coming down the other way. So you can see very clearly on the left here with this building, the error between the two perspectives is proportional to the range. So the further away you get from the road where we've surveyed from, you get a bigger discrepancy between the two perspectives. But after applying the bore sight calibration, both perspectives align.
Yeah.
So I'll hand over to Dieter.
Thanks, Jake. Thanks for this wonderful introduction in how a great INS solution helps improve collected data. And now let's have a short look. What does it mean if you want to set up a system? So you have now a LiDAR and you want to come to a complete solution. What you need for this is basically not that much. So we have here a nice example how a LiDAR system setup could look like. So you need only a few essential components like the XNAV 650 IMU. With the antennas, you need a LiDAR for sure. Computer for storage and monitoring would be great. The interesting thing is you saw examples from a PAC dataset. If you use, for example, our PAC VLP16 or VLP Lite for UAVs, with PACs, for example, it's quite easy to get the data handled just by the OxTS IMU VXNAV. So with the data rate, you can go for a while and get the data stored directly in the IMU system. If you go to solutions to sensors that give you a higher amount of data, that give you better LiDAR resolution, just for example, the Ultra PAC, you would need a computer for storing your data. So, and then to round up the setting, you need the software, the OxTS software, with all these nice features you heard about from Jake before. So for processing of the GPS IMU, the bore site calibration, so that you can end up with a nice point cloud data set. And this is basically what is required. So you have a sensor and you have an XNAV system, so you mount it together. You connect the devices and operate them together. You need to configure the XNAV. And there's a couple of other things you should consider, as we heard just before regarding a bore site calibration, but that can be done easily with not that much amount of time. And then you are ready to survey, to record, process your data. So that makes up for an easy integration. You can rely on PPS and MIA or PTP together with the XNAV 650, and you're ready to go. So it's no wizardry, but this is a stable, proven system approach that you can work with. And what you need, in summary, you download the data, the INS data from the XNAV, you download the raw data from XNAV or stored in your computer. You use the software to do the right trajectory calculations, you do the back and forth calibration, and hopefully you have access to GPS base station for post-processing. The better you want to have your data, it's recommended that you use this, and when you're ready to go. And well, if you like more info about that, both the guys from OxTS and we from Velodyne are happy after the webinar to provide you with more information on this. It's actually a simple system approach. So, we saw from a poll that you use a couple of different mapping platforms. So everything was listed from backpack to UAV, car platforms, or even boats. I saw, I think 20%, if I recall it right, were using in a maritime environment. So organize your power supply, set up the system with the antennas, the IMU, with the computer, and in the end, low-cost solutions start around 20k euro or so, and that's it. So that gives you a full package from the data acquisition, from the whole processing, that you end up with a nice and smooth point cloud that gives you reliable georeference information. So it's really versatile, it's simple, and it's cost effective.
So just finally then, we're going to talk about some accuracy estimations. So as Dieter mentioned, we use some software which is quite unique in the market, which is able to combine the raw data from the Velodyne sensor and the navigation data from our INS and to create a point cloud and to calibrate the setup between them. An important feature that we offer makes use of these accuracy estimations. So we have produced some diagnostics run by the Kalman filter, which combines the data streams coming into the INS to get an understanding of position accuracy. So with your INS device, it doesn't just output position east, north, and altitude. It also estimates the position accuracy north, east, and altitude, and also the accuracies in the heading, pitch, and the roll. And we can use these quite intelligently in the point cloud. So we can actually put this data in the point cloud using a formula to work out the you could say the accuracy or the uncertainty in the position of each point in the point cloud. So that's what we do, and you can see in these pictures here. So on the right, you can see a survey of a village road, and you can see how the highest accuracy is blue on the road because that's the closest to the INS, and the further away, because of the IMU error, as we've discussed, the less accurate it gets. So on the left here, you can see how it starts blue, then goes dark green, light green, yellow, orange, and red the further away you're looking. But on the right, you can see how this is really a useful feature. So you can see how the INS system has driven under this tree line, and it's obviously going to be losing satellite signals. And you can see how, so it's driven from the top here and gone down through the bottom. And as it's gone through this tree line, you can see that the accuracy has dropped further and further until it's come out of the tree line and it's got an improved accuracy. So this is really useful because you can see exactly where you might want to resurvey, or you might want to simply edit out points that are above a certain uncertainty. So perhaps you want your point cloud to have all its points below 10 centimeters of error in its position. You could just remove all those points. So this can be a really useful and quite unique feature. So we also have an example of a Velodyne survey used with one of our INS devices. So this is carried out by our friends Drone Zone, and they've done a drone survey of a bridge. And it's using a VLP16 LiDAR, XNAV 650 INS, and our georeferencer software. So you can see here the results of the survey. So they're looking for any damage in this railway bridge, any issues with structural integrity, anything like that. And so what they've done here is surveyed this bridge for some time. You're seeing a lot of different perspectives added up into this one composite image. So this isn't a single perspective. And so you can understand how the bore site calibration and the high degree of accuracy from the IMU are both extremely important as these perspectives are are added up. And you can see this comes straight out of our georeferencer software. You could do error analysis and things like this. As Dieter mentioned, the VLP16 data can be logged directly onto the 650, which makes for a very convenient drone setup, so you don't need a dedicated logging device. And of course, both devices are suitable for drone use due to their size and weight and power consumption.
Yeah, and these are very, could you quickly go back, please? Thank you. These are very impressive examples. So please think about that the examples are being derived from our lowest resolution sensor. So it is just a VLP16 that comes with angular resolution of 2 degrees. And it is a 16-channel laser. And if you look at the data, at the quality of the final processed data, you might at first glance think this comes from a much higher resoluted sensor. It reminds you on data that could be from a sensor that gives you more than 100 channels or so, but this is just a VLP16 coming with 16 laser channels with actually not that narrow angular resolution. So it is an impressive example what you can get out of the data, what quality of a point cloud you can get with the right INS solution and with the right appropriate processing software. And the more higher quality sensors you apply to get data, the better the final result gets. But think about, this is just actually, I would say, a low cost resolution that gives you outstanding quality. And I'm very happy that we can present these examples here.
Yeah,
Okay.
Thanks, Dieter. So we've just got a second poll question here, and I'll launch that now. So we just want to know if you are currently using a LiDAR setup, or you are thinking of using a LiDAR setup, have you considered, or are you using an INS device, or are you perhaps using some other navigation data source? So maybe just a simple GNSS system, maybe SLAM algorithms, or any other alternative. So I'll just leave that up for a few more seconds. Okay, thank you.
Okay, before we come to an end, please allow me to say a few words regarding our product lines. So we saw these nice examples from the PAC, from the VLP16, that price-wise more or less turned actually in a kind of a low-cost product. And it was great to see what outstanding quality you get from using a sensor like this. But there's more to it. We have more in our product portfolio. So we have the versatile Ultra PUC that gives you double the range as a PUC and double the number of laser channels. And we have likely the best possible 3D multi-beam LiDAR you can get in the world with the Alpha Prime. And we have coming products we just recently introduced, the Velodyne product line with models for near range and far range detection, and the upcoming Velabit solution that gives you the smallest form factor with very, very great resolution. And not everybody of you may be aware yet, with all the new sensors starting from the Alpha Prime, we enable PTP as well. So your options to use INS systems together with such a technology even are getting better and better. And again, do not hesitate to contact us anytime if you would like to get more technical information. Okay,
and
Jake.
just a word on the OxTS product line. So we offer some different INS devices to get your navigation data with your Velodyne sensor. So we've got a Survey Plus, which is a top of the line premium solution, particularly good for mobile mappings on a van or aerial plane based mapping, as well as the XNAV 650, which is a very economical, compact choice, and it's the one that a lot of the data we've seen today has come from. We've also got a board set version, which is able to get the same kind of specs if you wanted to integrate into your products. And we've got software. So NavSuite is our complementary software, which comes with our INS devices, which processes your data and gives you everything you need to work with the INS. But importantly, we have OxTS georeferencer. As mentioned, this is quite a unique piece of software, which is able to work with the raw data from the Velodyne units and produce point clouds, calibrate the setup, and has a number of unique value adds that can only be done at that georeferencing stage when the data is combined together. You can find on our website and on Velodyne's website a number of different things of interest. So you've got articles, got some brochures on exactly everything we've talked about and a bit more information. Articles as well available on our website if you want to have a look at those. Do follow us, Velodyne and OxTS, on social media. So we've got LinkedIn, Twitter, YouTube, and we do now have some time for questions. So if you've got some questions for Dieter or myself, please do put them in the box on the side there, and we'll try to answer them.
Thanks a lot for your time, Jacob. Thanks as well for joining us, Dieter. Yeah, we do have some questions that have come in already, but as Jake mentioned, if you do think of anything, then please feel free to ask them now. Yeah, like I said before, we will try and get through as many questions as we can. If we don't get to your question, then we will reply to you individually after the session. So the first question we had in, guys, was what is the practical difference between having the LiDAR installed horizontally as opposed to being tilted at a certain angle? Is one objectively better, or does it depend on your use case?
That's a question that's often being raised. You mentioned the answer in the second part, actually. So it's really depending on the use case. So in many cases, you mount on a moving platform. It could be a car, it could be a boat, whatever. You mount the sensor horizontally, so that with respect to the 360-degree rotating line of rotating field of view of a rotational sensor, you have it horizontally and look straight forward with 30 or 40 degrees vertical field of view. So the results will change if you tilt the sensor, if you move the axis. In some cases, it might be appropriate that you mount it with a different angle. If you want to get the utmost resolution for a survey, it might often be an option that you use two sensors. I saw that a lot of you are interested in backpack solutions. We have very nice, very reliable integrator solutions, which have been sold many times meanwhile, where you combine two sensors, one horizontally mounted and one compared to that with a 90-degree shift, or 45-degree shifted field of view. So the impact of this is quite clear to understand. You get more dense resolution and you get a better, denser depiction of the environment you want to map. But at the end of the day, it depends on the use case.
Thanks, Dieter. So second question, this is probably one for Jacob. Do you do a bore site calibration before every survey?
Not necessarily, no. So what is important is that each setup that you have, so each time you set up the devices, it is important to bore sight them. But for example, if you left them on the car after bore sighting, you would not need to bore sight it again, or on the drone. Perhaps it is recommended that every so often you do another bore sight calibration, because remember we're talking about points of a degree here, and it's hard to know if just temperature changes or vibrations of the road have rotated it in any way, very slightly. But in general, no, as long as the setup remains, you do not need to perform another bore sight.
Thanks, Jacob. Moving on to the next question. So what are the specs on the IMU you are using? Is it industrial, tactical, or navigation grade?
Well, we usually say that it is survey grade, so higher than the industrial grade IMUs. So the data that you've seen today, some of it has been for the XNAV 650, which has 0.1 degree in the heading and 0.05 in the pitch and roll. That is in real time. In post-processing, although we don't at the moment quote specifications for post-process specs, it is much better in post-processing. The Survey Plus is better than this, and again, even better in post-processing. So they are. We say that they are survey grade.
Thanks, Jacob. So the next question, what is the largest range bore sight Velodyne sensors can achieve today in a single shot?
So I think this is asking how far away can the Velodyne sensors see. So that might be for you, Dieter.
Well, it depends on the kind of sensor. So we have, for example, with the PAC family of products, 100 meter of range. We have with the Ultra PAC 200 meter, and with the Alpha Prime sensor, we introduced complete full range of 300 meter.
Thank you, Dieter. So next question, if we add a camera, what are the advantages, and how can image and point cloud be merged? If that's, that's possible.
I'll begin to answer that. So at the moment, our OxTS georeferences software does not combine RGB camera data into the point cloud. This is something we are looking to do in the future. For now, typically there's not much of an advantage for surveyors in doing this, unless they specifically want to know the kind of the colors of things they're surveying. But most applications, if they're counting objects or measuring volumes or distances, don't need this kind of data. If you did want to add it in, you can do it yourself. So you can take the data that we provide, the INS provides, and the Velodyne provides, and you would have to do a bit of coding yourself, but you can get that into the point cloud as well. I'm not sure if you want to add anything to that, Dieter.
Well, I'm fine. Thank you.
Thanks, guys. And yeah, another question. When a LiDAR is mounted on a drone, what are the most important sources of problems? Would you recommend gimbal-like stabilization for LiDAR to reduce vibrations and INS errors?
So you need to ensure that the INS and the LiDAR are rigidly mounted together. So you need to, if you are going to use a gimbal, you need to make sure that both devices are on the same side of the gimbal, if that makes sense. So they are not moving relative to one another. But the INS, of course, has better performance if there are lower vibrations. So if you can provide some kind of low vibration mount or whatever, then that would be useful. The INS also has to be, at least for now, it has to be rigidly connected to the antennas, so it cannot move relative to the antennas either. So a gimbal is not, it is possible, but it'd be a very complicated solution. So I would say no gimbal is recommended or even necessary. You saw that data with the drone. There was no gimbal on that. It was simply a fixed mount solution. And yes, on the drones, typically the antennas would be the biggest source of problems, I would say.
Thank you, Jacob. So yeah, I'm quite conscious of time, so we've probably got time for a couple more questions. So the next question: which parameters do you solve for in the bore sight calibration? I assume the 7 transformation parameters: dx, dy, dz, rx, ry, rz, and a scale factor. How accurate can these parameters be determined?
Yeah, so typically the bore sight calibration will be calibrating the 3 rotation angles. We do also have in georeferencer a feature that will calibrate the displacements. The displacements, it's a much more, first of all, it's much less important because it's an error that is not exacerbated by the range, but you're also, it's less important because you're going to have less error in it anyway. So typically you would be only calibrating the 3 angular rotations. How accurately can they be determined? It really depends on so LiDARs have different accuracies. The range at which you're viewing them limits the accuracy. So it's hard to say. You might say something like 0.1 to 0.3 of a degree, or better than this. It really depends on a number of different factors.
Thanks, Jacob. So yeah, if anybody has any more questions, please feel free to ask them in the question box now. I'll be moving on to the final question, and anybody who excuse me, anybody who has asked any more questions from now, we will come back to you personally, if that's okay. So final question: in case of GPS outages, how high a density point cloud and GPS values are tagged due to the low update rate of the GPS sensor as compared to the LiDAR sensor?
So actually there would be no decrease. So the INS data output rate does not depend on the GNSS. Because it has the IMU, it is constantly outputting data at 100 hertz, or you can have 200, 250 hertz data output. So that would be your data rate, and it's perfectly suitable for the LiDAR. There wouldn't be any drops of the data coming out.
Yeah, absolutely. It's independent if you use a rotational LiDAR or a direct solid state LiDAR array solution. So it works probably well because the refresh rate of your IMU outbeats the one of a LiDAR. So you don't lose any signal.
Perfect. Thank you, Dieter, and thank you, Jacob. So yeah, like I said before, if anybody has any final questions, please do feel free to ask them now. I think that just leaves me to say thanks again to Jacob and Dieter for taking us through the presentation. I hope everybody found it useful. And just to say again that in 24 hours from now, the recording of the webinar will be sent out to everybody who registered for you to watch back at your leisure. So yeah, thank you very much, Dieter and Jacob.
Thanks, Jeff. Thanks, everybody.
Thanks, Jeff. Thanks, everybody, for listening. And we would be glad if you would get back to us for further discussion. Would be nice. We're looking forward to it.